Okay, so today we're going to talk about rewriting some exponents and using fractional exponents. So we've worked with exponential functions, and we've done things like 2 to the second, and that's equal to 4. It's 2 times 2. Well, what about 2 to the 1/2? The 1/2 power is the same as the square root. So 2 to the 1/2 is the square root of 2. 2 to the 1/3 is the cube root of 2. I can look at this. So my root index, cube root, there's a 4th root, that's a 1/4. My root index, we call it. We don't write it for the square root. We don't put a 2 here. But the 4th root means what to the 4th is 2. A better one might be what to the 4th is, 4th root of 16. That actually is 2, because 2 to the 4th equals 16. Okay, so then the root index here is my fraction, or my bottom of my fraction. So if I'm doing this with x squared, so that can be x to the 2/3. My root index went to my denominator, my squared went to the numerator. I can also write that, I can do those in either order. So I can either do the cube root first or the squared first. That does not matter. So that allows me to solve an equation like 27 to the 2/3 without having to use a calculator. I can say that that is cube root of 27 squared. The cube root of 27 means what cubed is 27? That value is 3, because 3 times 3 is 9, times 3 is 27. So this is 9. 27 to the 2/3 power is 9. Okay. So we're going to go through some of our exponent rules, because we'll also apply these with exponents. So hopefully you know that x to the 5th times x to the 3rd. To do this, I simply add my exponents, and I get x to the 8th. Why is that? Well, x to the 5th is x times x times x times x cubed. That's 8 x's multiplied together. That is x to the 8th. I can apply this to fractional exponents. Again, all I'm doing here is adding the exponents. Now, I must add my fractions to add these up. So I'm going to add my fractions down here. 1/2 plus 2/3. I need a common denominator. That common denominator is 6. 1/2 is 3/6, because 3 times 2 is 6, so 3 times 1 is my 3 here. 2/3, 3 times 2 is 6, so 2 times 2 is 4. Add the numerators, 7/6. So this comes out to be x to the 7/6. So that's rule number 1. When I multiply with like bases, bases being my x's, I just add the exponents. When I do a power to a power, I multiply. And I get x to the 15th. Again, why is that? I have x to the 5th, and I'm cubing that, which means I'm multiplying it by itself 3 times, giving me 15 x's multiplied together. There's the rule. Here, I must cube both my 2 and my x squared. 2 cubed is 8. X squared cubed, following that rule, I multiply, I get x to the 6th. Again, I apply this to everything. 7 cubed is 343. I would expect you to use a calculator for that. And then I'm cubing all the parts. Again, multiplying the exponents there in the denominator. X to the 5th over x squared. I subtract. If I had it the reverse, again, I'm thinking of this as 5 x's on top of 2, or in this case, 2 on top of 5, leaving me with 3 left on the bottom. Here's the one that you might not be super familiar with. 1 over x squared. The negative exponent means I take the reciprocal. That applies this way as well. I take the reciprocal and I lose the negative. I will show you why. Next page here in a second. We'll look at the simple exponential function y equals 2 to the x. And we're going to make an xy table. 2 to the x means I'm doubling. I'm going to intentionally start here at 1. Y equals 2 to the x. So that means I'm doing 2 to the 1st, that is 2. 2 to the 2nd is 4. 2 to the 3rd is 8. Notice I'm doubling. Or if I'm going backwards, I'm taking half of 8 is 4. Half of 4 is 2. Half of 2 is 1. Half of 1 is 1/2. Half of 1/2 is 1/4. So 2 to the 0 equals 1. Anything to the 0 power equals 1. 2 to the negative 1 equals 1 over 2 to the 1st. 1 over 2. 2 to the negative 2 equals 1 over 2 squared. So I did the reciprocal. Okay. We can combine some of these rules and work together. We're going to do a little more practice with these in the future. We're also going to talk a little bit about reducing radicals here. Anytime I have radicals multiplied together, I can just multiply the inside. Now I can try to reduce. This one does not reduce. So I'll do one that does reduce. I'm going to show you 2 different methods for this. This is going to be roughly what the book shows you. So I'm basically working backwards to square root of 25 times square root of 3. Again, I'm taking factors. The reason I picked 25 as a factor is because the square root of 25 is 5. That is a perfect square, and I've reduced this to 5 times square root of 3. That's method 1. That's the method shown in the book. Method 2, I can pick any 2 factors. I'm going to choose different factors. I could choose 25 and 3. That'd work great. But I chose 15 and 3. It doesn't matter what my factors are. Now, these are prime numbers. I cannot factor 5 any further. I could factor 15, so I did it to 5 and 3. Once I get to prime numbers, or really anytime I get to pairs. Once I get a pair of 5s, I wouldn't even try to simplify it even if I could. The pair of 5s is like 5 squared. The square root of 5 squared, essentially it's this 25 here, is 5. So that comes out. Whatever is left stays inside. Square root of 216. I don't know these factors super well, so I'm going to do the tree method. 108, 2 and 108. I'm going to keep doing 2s. 54. 54 is 6 and 9. 3 and 3. 3 and 2. So I've got a pair of 2s here. Yes, there's another 2, but there's no 2 to pair it with. I've got a pair of 3s here. Again, no, there's another 3, but not a second one to make a pair. So I take my pairs and I bring them out. That's 2 times 3. The ones that do not have anything, I'm only taking from the ends of my tree, okay? Do not take the 6 or the 9, we broke them out further, or the 54, or the 108. So these circled ones came out. The non-circled ones are in, and this is factors, so I'm multiplying them. 2 times 3 is 6. Square root of 6. Not often they come out to be the same number, but this one did. Okay, that was our lesson from Thursday.